This is a tutorial of a computer program in a form of a rather long video, and it is intended for those people who are interested in trying my Slingshot setup designer. It is not intended to be interesting or fun. Hi everybody, this is Jazz from About Slingshot's YouTube channel. In my previous videos, which relate to internal and external slingshot ballistics, I mentioned my Slingshot Setup Designer, or SSD, the program which I made in order to be able to do various calculations related to slingshot shooting. This program was in the background of all the calculations in these couple of videos, and I promised in the last of these videos that I will make a presentation of this program, some kind of tutorial to show how it works. Well, it simply follows the physics of slingshots. So let us review main elements which we encounter when we speak about slingshot ballistics. First, we said there is a very special point which is somewhere halfway between your full draw and the fork tips, where the pouch stops accelerating the ammo and where the ammo receives its exit velocity and exit energy. The variables which determine this velocity and energy are draw power, the weight of the ammo, weight of the pouch, weight of the rubber itself, and elongation, which is, as you remember, the difference between your full draw and active bands. Then you shoot, and the ammo flies through the air and it confronts, and some other variables, drag coefficient, how much your ammo is aerodynamic, silhouette, or what is the size of that part of the ammo which confronts the air, shooting angle, how high your forks are from the ground, air temperature, air pressure, humidity as elements or variables which determine air density, and gravity. So any good software, I think, should take these into account in order to simulate the nature faithfully. So let me show you now the main screen of my program. And here it is. This is the main screen of my program, which I call the control center. And I must admit that it looks a bit clogged, but if we think in terms of slingshot ballistics, internal and external, it will become very familiar to you. We said that the first two important elements are exit velocity and exit energy, and here they are. They are determined by internal slingshot ballistics variables, which are draw power, the weight of ammo, pouch and rubber, and elongation, which is, as you remember, the difference between your full draw and the active bands, the length of your active bands. Then there is a group of variables which practically most of them determine the weight of this ammo. Just think logically and everything will be okay. See here, you can select in this program what you shoot: round ball, cylinders, cubes and so on, and those objects, they have dimensions. In this case this is round ball and its dimensions is 9.52 millimeters. And these 9.52 millimeters have their volume, which is 451, as you see in this case. And when this is multiplied with the density of the material that you are using, in this case steel, then these two numbers give 3.55 grams weight of your arm. Then this same number here, the diameter, determines the silhouette of your ammo, which is in this case 71 square millimeters. And if you divide the energy of this ammo with the silhouette, you get energy per square millimeter of silhouette. For some people and some shooters, very important. Then here is the first group of external ballistic variables, which is air temperature, air pressure, air humidity, and they together determine the density of the air through which your ammo is going to fly. This number, not these three numbers here, but this number of air density goes into the calculation of the trajectory. Then you have shooting angle, gravity, in this case Amsterdam. Then you have here drag coefficient, which I put here far on the left side because it is tightly connected to the shape of the object here. If you select round ball, then drag coefficient is 0.47. And these variables, this one, these and so on, these external ballistic variables, they come into effect when you click the shoot button, and then the trajectory is calculated. Here on the left side you have the group of variables such as the height of your forks, how high they are from the ground, the height of the target, the size of the target, and the distance of the target. And there is a group of elements which basically have to do something with automation. For example, in order to save your time, if you want to see how velocity behaves when you increase the weight of the armor, then you can do this elegantly for about 24 instances. You can go, for example, from 1 gram to 24 grams. Computer is going to calculate this for you, and you will see the results in a separate window. Then you click the shoot button, and then new window opens with all the elements of the trajectory, but we shall see this later. Then there is a group of commands which simply work with your file. This program can have two files in the memory. One is the default file, and the one is your file that you can load. Then when you load, your file is in. And then you can switch between default and your file. And this refresh button brings you back to the default values, either of the default file or of your file, so you can start afresh. The program gives you the possibility to work in an international standard or US standard, and all the calculations on this screen are done in real time. It takes some time to calculate the trajectory, but this is a separate issue. Now, this picture that you see here is a screenshot of my program. In order to go deeper into the workings of this program, I suggest that we switch now to live presentation. And here it is, Slingshot Setup Designer. Let me first show how everything is interconnected here and calculated in the real time. See, when I change draw power, you see how many things change around. Exit velocity, exit energy, the weight of the rubber, the total weight, and energy per square millimeter of silhouette. All variables here which are interconnected work the same way. So let us go now step by step. The first group of commands here relate to draw power. Let me refresh the data. When I change the draw power here, velocity and energy change, but also you see the width of the rubber changes. So if I measure my rubber bands, if I take the elements of my rubber bands and say that there are two bands, 2 centimeters wide each, in total it is 4 centimeters, as you can see here, and their draw power at stretch ratio of 5 is 4.67 kilos. Then when I change the draw power, so when I change the draw power, the width of the rubber changes also. Let me be more precise. 4.67 kilos, I have 40 millimeters wide bands in total. And the weight of these bands, of active part of these bands, is 3.8 grams. If I double the draw power, this number here should be double, and this number here should be double. Let me show you. The double of 4.67 kilos is 9.334 kilos. So let me come to this number. You see, 9.334 kilos, 80 millimeters, 2 times of the original width, and 7.6 instead of 3.8 grams. So this program takes all these variables into account in order to calculate your exit velocity and exit energy properly. These arrows show, these yellow arrows show, for example, that draw power influences the velocity, and this white arrow shows that it influences the weight of the rubber. Here is the unlock button. See, if I do not want to calculate the weight of the rubber when I change the draw power, I simply click on the unlock button. To be honest, I have no idea why I made this, what this can be used for, but let it be for now. The second group of parameters from internal ballistics is the weight of ammo, pouch, and the rubber itself. I can set ammo weight to 0, which means that I only have rubber and the pouch, and in that case the velocity and energy are 0, of course, because they relate to ammo velocity and ammo energy. However, if I click here, I get the energy of the setup, in this case 97.33 meters per second, and setup energy of 22.73 joules, if you fire it without the ammo. I can set also the pouch weight to 0, and then the setup velocity goes up to 120.24 meters per second and setup energy to 27.47. I can copy these data for later use in a spreadsheet maybe, and I can save them. The weight of the rubber cannot be set to 0 because calculus would not make sense. Smallest value is 0.01 gram. And whatever I do here or here or here reflects itself in the total or joint weight of these three elements, and then this number goes into the calculation of exit velocity. The third element which determines the exit velocity is elongation. However, in this program you do not manipulate the elongation directly, but indirectly through manipulation of draw length and stretch ratio. When you do that, either this or this, you see the length of active bends and elongation are calculated for you. Let me refresh the data. In this case I have 75 centimeters of full draw. Under a stretch ratio of 5, my active bends are 15 centimeters, 75 divided by 5, and my elongation is 60 centimeters, which is 75 minus these 15 centimeters. And then this number 60 goes, you see this yellow arrow, into the calculation of velocity. And again, in much the same way as with draw power, there is this white arrow which goes from active bends to the weight of the rubber. Logically, for a given width of the rubber, if you extend the length, then the rubber is heavier. Let me show you. Let us say that we extend my draw of 75 centimeters to 150 centimeters. That is, we double it. Now, on the stretch ratio of 5, my active bends are no longer 15 but 30 centimeters, and this is reflected here in double the weight. And of course, my elongation is now not 60 but 120 centimeters. One last remark. When you do your measurements of physical rubber, of the rubber that you want to analyze, then first I suggest that you first set draw power, then the width of the bends, and then the weight of the bends, then the length, then your draw length and stretch ratio. Then when you change whatever here, all the other elements, is exit velocity and exit energy, will be calculated properly. One final remark. This program works not only with the bends but with the tubes too. Except that it does not work with the widths of the tubes. There are no widths like 4.6, 4.7, 4.8 millimeters and so on in tubes. They work differently. But you can work with the number of tubes. For example, if I say that my draw power is 2 kilos and I have 2 tubes, one on each prong, then doubling the power to 4 kilos, I get the number 4 here, which means 4 tubes or 2 tubes on each prong. Not really anything spectacular, but what else I could do. However, I might do a video on differences and similarities between bends and tubes, hopefully. Another thing is, this program does not work with tapered bends or tubes. The simple reason is that I could not find any valuable math behind tapered bends or tubes, therefore I was not able to program it. If I find, or if you know, or if you have a lead, then please inform me, and I might incorporate this math into some future version of this program. Thanks. Most of these elements on the left side here, they determine one single parameter, which is the weight of the arm. Let us go step by step. First, here you select what you are shooting: round ball, short cylinder, long cylinder, or cube. So let us say I select ball. Then this is the diameter of this ball, in this case 9.52 millimeters. And of course you can go either way. Then there is a list of common materials with the value of their density. In this case steel, which is 7.86 tons per cubic meter. When you set the dimension of your round ball, it is its diameter of 9.52 millimeters, then the volume of this ball is immediately calculated, here 451.53, and these two values are multiplied and you get 3.55 grams for the weight of your armor. Also, when you set the diameter, the silhouette or the cross section of your round ball is calculated immediately, and in this case it is 71.14 square millimeters. And since we have already calculated energy and silhouette, then when you divide energy with the silhouette, as here, you get energy per square millimeter of the silhouette. Some people would like to know this. Now we come to the external ballistics parameters. Here I have air temperature, air pressure, and humidity. And all these three parameters, they affect the air density, and this air density goes into the calculation of the trajectory, not the temperature, pressure, or humidity. And as a curiosity, here is a button which in this case says air is on. When you click, the computer will simulate the flight of your armor, but not through the air, but through the vacuum. Gravity is set here for Amsterdam, but you can select many towns in the world and set the gravity manually. Shooting angle is in default set of parameters 45 degrees, but you can also change the way you need. And the last element, which affects the flight of the ammo, not exit velocity and exit energy, but the flight of the ammo, that is its trajectory, is drag coefficient, which for the round ball is 0.47, and if you change, for example, the cube, it is then 1.05, or you can set it by yourself. When you have all your elements set up, then when you click on the shoot button, a window will open up where on the left side here you have so-called flight data. And this is the range, you see, this is every meter of the range. In this case, this is 171.5 meters. This is height of the trajectory of your armor in the flight, velocity and energy. And here, if you can see this graph, you see this is the trajectory, this is velocity, this is energy. And this number here says that in order to see this in real proportion, you need to extend the horizontal value by 2.8 times. Or you want to save this picture, the program suggests the name of this graph, and in this name you have number 1383, 1383, which means in order this graph to be proportional, its horizontal value has to be 1383 pixels, if you have a program which can do that. This section here I call statistics. These are the main elements from the main screen here recorded, like density, which tells you which material is that, diameter, volume, draw power, and so on. And if I change something here on the screen, let's say I change the weight of the ammo and click shoot again, then again and again, then I will get a window where again on the left side I will have the flight data from the last shot, but here you see the columns. This is the statistics of every shot recorded. As an example, I had ammo weight of 5 grams, 7 grams and 9 grams, and the range of the first is 182, 181 and 172 meters. Exit velocity for the first shot is 58.9, 52.6, 48.05 and so on. And you can have 24 of these columns or shots if you want, and in each case here and here you can copy data, copy stats, copy data here, and you can save them. Let me show what you can do with this copy function and Excel, for example. So I paste the data, then I can highlight this data and insert a graph which I find suitable. Of course you can do averages, minimum, maximum values and so on, whatever a good spreadsheet allows you to do. This group of commands is very interesting. This D stands for dump. So whatever you do, for example, you change the weight of your ammo to 5.55 grams, the velocity changes, energy changes and so on, you simply click on dump. And all the relevant data from the screen are recorded here. Then you do something else, whatever, click dump, and then there is another column of all the relevant parameters from the screen. So you can go on 24 times like this, and again, you can bring this data to spreadsheet or save data, manipulate in whatever way you want. This button 1D stands for one-dimensional. What does it mean? Let us say that you want to see how the velocity of your ammo changes when you have heavier and heavier pouch. So you start with 1 gram, you click on 1D, and you say that here you have the choice of various elements what you can change. So pouch weight in absolute terms, you click and you ask for the change of 0.1 gram on top of the pouch weight where you started from, on top of 1 gram. You select number of steps, let us say 9, because 9 plus the original one will be 10 in total, and then you say go. So you see pouch weight is 1, then 1.1 gram, 1.2 grams, 1.3, and sometimes you have to click on this window to refresh it, and velocity changes from 65 to 61 meters per second, which means that heavier and heavier pouch takes some energy from setup, therefore ammo velocity becomes less and less. Again, you can save it, copy it to clipboard, bring it to some other program, spreadsheet, and you can show all these values but in US measurement system. 2D means two-dimensional. Simply, if you want to change two variables at once, not one, as in 1D, then you use this button. Let me show you what it can do. So, this is a window where you say which two variables you want to change. The scope is limited here. You have only three combinations, ammo weight and draw power as independent variable. Elongation and draw power, and ammo weight and elongation. That is all three combinations of the three internal ballistics variables. And for each of these you can calculate the velocity or energy per reference area, that is the area of the silhouette. Let us try now this first combination, ammo weight and draw power as independent variables, and then we see how the velocity behaves when we change these two variables. I select the number of steps for each of the variable, let's say 5 each. Here I have statistics of the variable x1 is ammo weight, 3.55 grams. x2 variable is draw power, which is 4.67 kilos. By the way, the program takes as the starting values, those values which are on the screen, okay? And the dependent variable is velocity. And I say that I want to do the changes in 10%. So 3.55 grams goes to 10%, 20, 30, and draw power also goes from 4.67 kilos, 10% up 5 times. So we say go, and that's it. This header here is ammo weight, this is draw power, and these are the velocities. I must admit that this is not so visible here, so let us go to the spreadsheet. So I paste the data into the spreadsheet. This row here is unnecessary, and I do what I can do in spreadsheet, like this. So I separate the headers, ammo weight and draw power from the calculated velocity. I can take this and bring it into a graph, and from here on you are on your own. Before I go into explaining target shooting, let me say something which I forgot when I started this presentation. Ammo weight you can set in millimeters or in fractional inches, like this. You see 3.8 inches is 9.52 millimeters. And everything is reflected in decimal inches. Also, all these weights, rubber, pouch, ammo and total weight, in international system are in grams. In American system they are in ounces, except for ammo weight, which is in grains. But of course they are recalculated here into ounces. And the third thing I have to come back to is something about the stretch ratio. This program understands that you will set your draw power with the corresponding stretch ratio. As you probably know, when you stretch the same piece of rubber 2, 3, 4, 5, 6 or 7 times, the draw power is not the same, it grows. And not even on a straight line, but somehow curvy. So when you say that you have the draw power of 4.67 kilos under stretch ratio of 5, then that's it. You can change stretch ratio here, you see, but the draw power should go up or down together with the change of the stretch ratio, and it does not. So if you want to play with the stretch ratio continuously, then you can click on this button here, and it will open up a window which allows you to load in your stretch ratio file, or you load the default file, which I'm going to do here. And in essence, this file is a plain text file. You have stretch ratios here and the draw powers here. For a more detailed approach to this, please read the user manual that I distribute together with this program. But when you say now use function now, the stretch ratio will come back to the lowest stretch ratio, and then you see this is 1.4.8 kilos. When I go up to 3, draw power goes to 2.3 kilos. I go to 4, it goes to 3.3 kilos, 5, it goes to 4.67, and so on. And now you have the full working and interconnectedness between draw power, stretch ratios, and so on. Target shooting in this program is done using these 4 commands here. The first is forks height, that is how high they are from the ground, and they can go to 100 meters. Then the same for the target height. It also can go to 100 meters up. Then the target size. The default is 25.4 millimeters or 1 inch, and it can go to 10 inches. And finally, the target distance, which by default in this program is 15 meters, but it can be 1 meter or 100 meters. Let me refresh screen. And when you click on this button, target window opens, which gives you the basic statistics about these values here. And this red dot represents or simulates the crosshairs, and it is directed toward the center of the target, no matter how high or how low the target is. Let me explain. And this is it. There are three targets. One of them is horizontal to the forks, one is higher, one is lower, the distances are different, and so on. And when you open the target window, as you have seen a moment before, the computer automatically directs your slingshots toward the center of the target. And this red dot, which represents the crosshairs, is at the center of the target. Now, your task is to move your slingshots up to direct it to a new position, higher than the target, so that when you fire your slingshot, your armor will follow a given trajectory and hit the target. And this is basically what you do on this window. Let me go back to the target shooting window. So here it is, crosshairs pointing directly at the center of the target. And it will be the same if I put a target at a height of 3.5 meters. Again, the slingshot is directed at the center of the target. And here the computer tells you what angle is that based on the distance and the height. And of course, in order to hit the target, I need to elevate the slingshot. I do it here with this command. You see, I go up by 20 millimeters or by 1 millimeter. And then I say shoot. And I get a window which we are going to discuss later. And this black dot represents the hit. And it is below the center of the target. So I can go up more. Again, I say shoot. And it is now a bit higher than the center of the target. So I will do this. I will say to center, which means that my crosshairs will be directed again towards the center of the target. I will do a couple of steps up, shoot, and my hit is here. Now, the computer tells me try with crosshairs at 267 millimeters above the center of the target. So I accept that, and then I shoot. You see, I hit the target, but not completely. This is 0.001. I missed the target by 1 millimeter, lower than the center of the target. So I accept another suggestion. Then I shoot, and here is 0. There is no difference, between the height of the shot and the center of the target, and which means that I am on the target completely. So sometimes you do it for the first accepted computer suggestion, sometimes it is second or third try. You can copy target data, directly paste it in a spreadsheet or word processor, save this data, and there is window, practically the same window as we have seen when we did the long-range shooting, where you have flight data and the tries. Each shot at the target is written here with all the statistics, but we are not going to that. Again, you can copy data, save data from both tables and so on. There is something that I have to draw your attention to. I will copy this data, see, and I will open up the spreadsheet. So here I am in the spreadsheet. I paste the data, and you see here I have a new column which is called target height. So if I want to see my trajectory, I will first hide these two columns of the velocity and energy. Then I will highlight these three columns. You see, these are the target data, 15 meters. The height is 3.5 meters. Then I can graph. You see, this is 1.5 meters with the height of the forks. This is 3.5 meters of the height of the slingshot. This is 15 meters, although it does not look so, because this is not a proportional graph. It has to go way beyond the screen to the right, and not even this is enough. And the last thing I want to show in this video is number of calculations per 1 second of flight. By default, it is 100 calculations in 1 second, but you can change this to 1000. But then, for a longer shots, expect a very long time for calculation. So this is basically it. If I ever do a new version of this program, and I might. First, I would need some comments from the users. And there are a couple of things I already know that I will have to program in, such as when I calculate trajectory and the armor goes up and falls down, the air pressure is not the same at every point, and this is not programmed into the code, although I have this math. I simply forgot. The same is with gravity. Air pressure and gravity are taken account in this program only at the spot where you shoot your slingshot and not dynamically as the armor goes through the air. But basically, I am more convinced that internal ballistic elements, which end up with exit velocity and exit energy, are more precise, more accurate than the calculation of the trajectory. Trajectory can be plus minus a couple of meters up or down, but one thing is for sure, that even if the calculation of trajectory is not completely precise, the data that you get between various armor, for example, lead ball of 9.5 millimeter and steel ball of 9.52 millimeters, the relation between them is correct, I believe. If you came to this point of this long and not so interesting video, then I'm very thankful to you, and all I can say is thank you for watching. And I won't even urge you to subscribe.